This is Gibbs free energy and thermodynamic favorability, topic 9.3. Hashtag not sponsored by Nintendo, the Super Mario Bros. Movie, or anything like that. So the main objective here is to explain whether a physical or chemical process is thermodynamically favored based on the evaluation of Gibbs free energy. Or the change of Gibbs free energy. So this is a chemical process in which all reactants and products are present in a standard state, and it's given a specific symbol. It's delta G, and then the degree symbol at the end. The degree symbol means standard. So we're going to have to look at a couple of different things in order to be able to understand this specific topic. And if you can see that we have a couple of equations here in the bottom that you're going to have to know fairly well. And we'll get into these in a little bit. Gibbs free energy, G, describes the energy available in a system that can be used to do work. By calculating this, we can determine if the system has enough energy available to undergo this specific process. And this is where the term thermodynamically favorable comes in, or spontaneous. So enthalpy and entropy, they help determine if a reaction takes place. I need to account for both of these here in this particular thing. If reaction is considered thermodynamically favorable, then that means the reaction will take place. But it doesn't tell you how fast it will be. Sometimes they're slow, like rusting of iron, and it means it's under kinetic control. Enthalpy describes the energy required or released in a physical or chemical process. We know that if it's exothermic, exothermic ones are favorable. Delta H will be negative. Entropy is the amount of energy as a function of temperature that is not available for work because it is lost to molecular disorder. And we know from the second law of thermodynamics that if it's an isolated system, the sample will arrive at some thermodynamic equilibrium where the entropy is the highest. Sounds like my classroom sometimes. Processes that move to greater entropy are favored, so delta S equals positive. So there are a couple of things here that are kind of referred to. So Gibbs free energy, enthalpy, delta H is negative where it's favored, entropy, delta H is positive and it will be favored. In some cases, it is necessary to consider both enthalpy and entropy to determine if a process will be considered favored. If we have freezing of water, water releases, when it's freezing, it releases energy and delta H is negative, but the particles have more order, so therefore there's not as much entropy. When the temperature is less than 0, it will freeze, therefore delta G is negative. Gibbs free energy standard is negative. But if the water is over 0 degrees Celsius, the water does not spontaneously freeze. The Gibbs free energy standard will be positive. Likewise, let's look at sodium nitrate being placed into water. It's considered an endothermic reaction because the process absorbs heat from the water. That means delta H will be positive and unfavorable. However, there's more disorder, so entropy is higher. And we know that standard temperature at standard temperature the process is considered spontaneous, so it's going to be thermodynamically favorable. Delta standard Gibbs free energy will be negative. So from here we can see we have a couple of factors to consider if we're determining if something is considered favorable or not favorable, thermodynamically speaking. We need to be able to calculate the entropy change of surroundings. So when an exothermic reaction takes place, heat is transferred to the surroundings. They in turn increase in entropy due to the added energy. When the temperature is already high, there's less change when it absorbs heat. And when the temperature is low, there's more change in entropy when the surroundings absorb heat. So this means that entropy of the surroundings is proportional to the enthalpy and inversely proportional to the temperature. So for the AP exam, being able to derive this equation is not necessary. So, named after some guy named Gibbs, of course, because why wouldn't it be? So the equation is Gibbs free energy equals change in enthalpy minus temperature times change in entropy, or times entropy. For reactions that are thermodynamically favorable, Gibbs free energy is going to be less than 0. Always check your units. Delta H is typically given in kilojoules per mole, and delta S is given in joules over mole time Kelvin, which you saw last unit. So be sure that you are converting your units to the same unit. Probably the best thing to do would be to convert your joules to kilojoules. We know that if temperature increases when the entropy increases, so an increase in temperature would also magnify the entropy. Since we know that, the entropy is the energy that is lost to the system that is unavailable for work, we can subtract the T times entropy term from the enthalpy of reaction. That gives us and it will give us the energy that is available to do the work of the process. That's the Gibbs free energy. Delta H and delta S values will be provided. The temperature must be in Kelvin. I don't know why it looks like that, I'm sorry. When entropy is favorable, delta S is positive, but enthalpy is favorable, the reaction will always be thermodynamically favorable. When the entropy is unfavorable, so it's negative, and the enthalpy is unfavorable, when it's positive, the reaction will never be considered thermodynamically favorable. In general, the temperature conditions for a process to be thermodynamically favorable with Gibbs free energy be less than 0 can be predicted from the signs of your enthalpy and entropy. So if you look at the box here, we only need to calculate Gibbs free energy to determine the thermodynamic favorability if one of the terms is considered unfavorable. So the first one, it's all favored, meaning that you have a small enthalpy, a greater entropy to have Gibbs free energy that's less than 0. That's what we want to have. At high temperatures, if entropy is favorable, the T delta S term will be greater than the unfavorable delta H term, and the favorable entropy will dictate the thermodynamic favorability. That's a lot of favorable words in there. At low temperatures, if the entropy is considered unfavorable, the T delta S term will be smaller than the favorable enthalpy term, and the favorable enthalpy will dictate the thermodynamic favorability. So we can calculate Gibbs free energy for reaction when all the reactants or products are in their standard state. It's considered a reference point for all substances. Gases are at 1 atmosphere, solutions are at 1 molar, and the temperature is 298 Kelvin. To indicate that they are considered at standard, you're going to put a small circle, the degree symbol, next to it. Standard state differs from STP because STP occurs at 273 Kelvin, standard temperature and pressure, etc. In order to calculate the Gibbs free energy, we have to compare the Gibbs free energies for the formulation of the products with Gibbs free energies for the formation of the reactants. Those will be given to you. So the reaction, we can also use delta G, standard, or the reaction equals the sum of the delta G final of the product standard minus the sum of the delta G of the reactants standard. Whew, that's a lot. The decomposition of hydrogen peroxide H2O2 occurs slowly at room temperature according to the following reaction. Predict the sign for delta G using your, justify your answer. So this says that it occurs reaction occurs slowly at room temperature. So over time, this is going to happen. So delta G would be considered is negative. The reaction occurs spontaneously over time. Therefore, energy must be available or must be present for the reaction to occur. So predict the sign for delta S, justify your answer. So if you look at the reaction, there are more moles of gas in the products compared to the reactants. So delta S is positive. The products, I'll say the reaction has more moles of gas in the products. Gases have the most entropy. So entropy is increased. Consider the following reaction. Calculate the value for Gibbs free energy standard and determine if the reaction is considered thermodynamically favorable. So the equation we're going to use, delta G reaction standard equals the sum of the delta G of the products minus the sum of delta G of the reactants. Run out of space, sorry. So we have our delta G, kilojoules per mole. So I will tell you there's no Kelvin here in the units. So there should be, the unit will be kilojoules only for this. So delta G reaction equals, so it's kind of like before from last unit. You have to take your coefficients into consideration. And also notice how a couple of them are 0, so thank God. Don't have to worry about it too much. So it will be 2 moles of H2O times negative 237.2 kilojoules per mole of H2O. That's why the moles cancel out. Oh, I'll put this more parentheses, plus 4 moles of CO2 times negative 394.4 kilojoule over moles. Oh geez, plus 2 moles of N2, 0 kilojoules per mole, minus 4 moles of HCN times 121 kilojoules per mole, plus, so I'm running out of space again, plus 5 moles of O2. Multiply that by the delta G for N2, which is 0. So parentheses, brackets, this will equal negative 2,536. So notice how one of my delta G's don't have decimal places. So that's the least number of decimal places, or numbers after a decimal, I guess. So it's a whole number, so you're not going to put any decimals. Unit is kilojoules. So is this considered thermodynamically favorable? The answer is yes. Alrighty, if you have any questions, please let me know. Thanks.